never solvable exactly in no cases, except super simple, highly symmetric, like simple mass, spherical mass is one of the few cases in which you can find the exact solution. I told you when you work in weak field approximation, which is almost always the case, except close to the boundary of a black hole, very close to a neutron star, you have fields whose size is comparable to the diagonal elements. Generally, if you write G mu as the special relativity tensor, which is G0, which is the standard Minkowski space metric, plus a term, that term is always small, so you can write Einstein equations in first order approximation of that linear term, and you find wave equations. So in space, in vacuum, Einstein equation become the usual D'Alembert equation for each of the tensor component. So they admit wave solution exactly like Maxwell equation. These wave solutions are called the gravitational waves. They are, as we show, indirectly known to exist, but no direct detection has been done so far. Because they are super small, as we will see. The gravitational equations correspond in the language of quantum field theory in states of spin 2. They have two polarization states like the photon, but they correspond to spin 2 particle, the graviton, if the graviton exists, because don't take it too seriously. The graviton is not known to exist because we don't know if a quantum theory of gravity makes any sense. We have no experimental fact that tell us that we should treat the gravitation as a quantum field theory. There is a lot of literature on that, but there is no real reason to do that. When you do a quantum, when you quantize gravity, you are assuming something that we don't know. Namely, that quantum mechanics and gravity must be left the same when you try to quantize. We simply don't know. We have no experimental fact that tells this. So, in my opinion, the very concept of quantum gravity is something that goes beyond our knowledge. Maybe the right theory is not a quantum gravity, it's something completely different. But if you interpret gravitational waves equation as you treat normal fields, you find immediately that the graviton should have spin 2 and should be massless, because the wave equation we have seen before is the equation of the massless particle like the photon. That equation is exactly the same equation as the photon. By the way, the general covariance of the theory, these are 10 nonlinear equations, but actually only 6 degrees of freedom are present, because, as you know, general relativity is based on the principle of equivalence, but also on the general covariance. You can use any coordinate. So you are free to choose 4 arbitrary functions and perform a transformation of coordinates. this is somewhat similar to gauge symmetry in quantum field theory. So there is a kind of a mantra, totally unproven, but it's an option, it's a theoretical option, that you can consider general covariance as a kind of gauge symmetry and use this analogy to go somewhere, but this somewhere is unknown because nobody has gone anywhere so far, so we don't know. But this fact that you have spin 2 with only 2 polarization states makes some difference between electromagnetic waves and gravitational waves. In particular, while you can have radiation from a dipole in electrodynamics, a single moving charge can emit radiation. A single point of mass like that does not emit gravitational waves. You need a quadrupole minimum to emit gravitational radiation. This is important because it makes the emission even smaller than what you would expect. Covariance, that we call it gauge symmetry of gravitation, forbid a dipole to emit gravitational waves. The minimum is a quadrupole, which creates the interesting fact that you can do the calculation of the emission of the dipole much the same way as the emission in electrodynamics, because the equation, except for polarization states, because instead of having a vector, you have a tensor here. Okay. In electrodynamics, you have the Lambertian of for potential A equal to 0. In this case, you have the Lambertian of a tensor. So the polarization of the gravitational wave is different, but the behavior of the equation is similar. So you can do very similar calculation, and you have a dipole plus a quadrupole. But the dipole does not emit in gravitational waves. So the minimum term is this, and you pay 2 prices. The 5th power of the speed of light instead of the 3rd, and the 3rd derivative instead of the 2nd. It is the acceleration that drives electromagnetic waves. In gravitation, an acceleration is not sufficient. You need the third power, the 3rd derivative. No surprise. Acceleration by the principle of equivalence can be cancelled by a coordinated transformation. So, for a mass, accelerating is not enough to emit radiation, because the acceleration is not a universal concept. It depends on the coordinates. And the principle of equivalence say that you can always cancel the acceleration choosing the coordinate appropriately. You need the 3rd derivative, so the emission is strongly reduced. And this is the problem. What does it mean? H is a metric. You know that corresponds to a distance. We will see later what does it mean, but you see some numbers. If you take a large mass and you make it physical, so for example 1,000 tons at 4 Hertz, which is would be already challenging to do. Okay, you would get 10 to the minus 30 in power. 10 to the minus 30 watts. So there is no hope whatsoever to produce gravitational wave emission by lab-scale experiments. And even astronomical objects are very difficult, extremely difficult. because although you have quite a large amount of power, they are far away, of course. And you see that the metric change, take this as a typical value of the strain, okay? So instead of the Minkowski metric, you remember the first approximation, instead of 1, you have 1 plus a small number. This small number is 10 to the minus 18 if you have a source in the galaxy. 10 to the minus 18. You have to be careful. What does it mean? It means that if your metric is eta plus h and the length is this one, the effect on the length is related to this 10 to the minus 18. If you do the calculation, it means that you are linear, because it's very small, so the linear approximation is fine, and means that 1 meter is changed by 10 to the minus 18 meter, which is 1,000 of the diameter of the nucleus. So if you have a kilometer, you change your length by the diameter of the nucleus. You have to be clever to measure that. If the event is somewhere in a galaxy close by, the Virgo cluster is the closest clusters of galaxies. So if you wanted to integrate over 1 million galaxies, you will have to have a sensitivity that reach the Virgo cluster. That's not by chance that, of course, the Virgo project calls himself Virgo, because it was designed with the goal of having a sensitivity to reach the Virgo cluster. Why the Virgo cluster? Because if you look at the distribution of the galaxy in the nearby of our galaxy, you see that there is essentially nothing until you reach the Virgo cluster, and when you reach the Virgo cluster, you get a very large number of galaxies available. So in that case, you can hope that you have statistics to find some kind of event. We will see what kind of event can emit gravitational waves in this system. So the goal for experiments is to design a detection device that has the capability to observe a length variation of something at the level of 10 to the minus 18, a previous generation, in which there was the hope to observe galactic events. 10 to the minus 21, 22 is this generation, in which the Virgo project, the LIGO project, and the Virgo Advanced and the LIGO Advanced wants to be able to detect events up to the Virgo cluster. General problem: how many interesting events happen in the universe? Answer: we have no idea. We needed to make some estimates, we have to make some models, but actually we don't know. This is important to remember, because unfortunately, if you detect gravitational waves, of course you prove finally that general relativity is right. But even more important, because this is not that important, because nowadays very few people believe that gravitational waves could not exist. The indirect detection that I will discuss are already very convincing. So it's not really a problem of proving general relativity is right, which nobody doubts. But in order, the real goal is to get another astronomical tool, because detection of gravitational waves would be a beautiful additional tool for understanding physics. So the key point is to prepare the field for future gravitational waves observatory. Even better instruments that are able to, in case of several events like neutron star formation, pulsars, collapse of black holes in clusters of galaxies, many possibilities are potential emitter of gravitational waves, and it would be extremely valuable to be able to see these events. Gravitational waves are detectable. If you do the calculation with the general relativity, you see that the second time derivative of a length of a segment is essentially the Riemann tensor multiplied by that segment. And this can be related to the second derivative of the metric with respect to time. So that is the typical way to do it. You have two masses, and the distance between these two masses is changed by the flow of the gravitational wave. There are essentially two techniques that have been used to detect gravitational waves. Historically, the first is the so-called resonant system. You have an oscillator, typically a bar, a very massive bar, a rigid massive bar. So this drawing is an oscillator, two masses and a spring, but actually you take a rigid bar, so you have a large mass and a very large spring, because it's the rigidity of the metal. So your first oscillator is just a solid bar. Then you use the trick that if you couple two oscillators that has the same coupling but very different masses, the amplitude of the second mass, of the small mass, is amplified by a large factor that we will see in a moment. This is a typical trick used to amplify the signal. The oscillation that is in this resonator couples to the oscillator in the small resonator, and if you do clever the coupling of the constant and you take a much smaller mass, the much smaller mass gets the same energy, and in order to get the same energy with the much smaller mass, you need a much wider amplitude. So you make an amplifier. What is a super tiny oscillation of the resonant bar becomes something that you can hope to measure with the second oscillator. This is the principle of the resonating bars. Usually the second coupling is an electromagnetic system. It's not a spring, but it's an electromagnetic transducer. But the concept is the same. Another way, which is potentially much better, although there are features of the resonator that are still interesting, but the sensitivity is much lower, is the interferometer. The interferometer is essentially the repetition of the Michelson-Morley experiment. In this case, if you don't want to extract the ether speed, but you want to observe the interference fringes that are produced by the fact that when the gravitational waves arrives, will start to oscillate this length and this length in a different way, which depends on the direction of the gravitational waves. This is very important because the interferometer has also the capability to observe the direction, because the two arms oscillate in a way that depends on the direction of the wave. Of course, if you have a two-arm interferometer, you cannot reconstruct the direction. You need more than one interferometer to reconstruct the direction properly, and to reconstruct completely you need 3 interferometers of this kind, because each of them essentially gives you a plane. So if you want to get the exact direction of the incoming wave, you need to observe with the 2 different interferometers. So these are the very basic principles. Then we discuss a little bit more in detail what kind of objects emit gravitational waves. First of all, gravitational waves are even better than neutrinos in coming out from the very dense objects. They cannot be shielded by anything. So they arrive as they are emitted, independently of the amount of matter, of the density of the material they observe, because they are coupled to matter even less than neutrinos. Okay, the neutrino matter cross-section is 10 to the minus 41 at 1 MeV. The equivalent cross-section for a graviton is at least 10 orders of magnitude smaller. So gravitational waves are not shielded by anything known in the universe. So even the super dense material that you have within neutron stars or black holes cannot shield gravitational waves. So for this they are extremely interesting for astronomy. These are examples. In principle, if you had a sufficiently good detector, you could observe gravitational waves from supernova, from neutron stars, from a couple of neutron stars that spin one around each other and finally fall one within each other, the so-called coalition binaries, which are the most promising candidate. And then you could have gravitational waves randomly from the whole universe. These are dreams, because we have detected none of them, but in principle you can immediately tell that if you could detect these signals, you would immediately have a huge amount of information. Another thing that it's important that you notice is that these drawings are just for fun, because actually we don't know what signal we should expect. The only case in which the signal is relatively well understood, because it is super simple, is the coalescing binaries, because in this case, if you have two neutron stars that are falling one within each other, they are essentially 2 point-like masses that go in an orbit. So that problem is very difficult in general relativity, but tractable, because it's the simple dynamical problem you can imagine. And actually it can be solved. So the prediction of the signal you expect in the end of the formation of this gravitational wave is not completely unreasonable. You see the scale. 0, 0.1 second. Okay, so it's about 100 millisecond signal. You expect a periodicity that is more and more fast because you have the neutron star that is falling within the other one, and of course it gets higher and higher angular velocity. But that is the only case. The others are strongly model dependent. For example, the spinning neutron stars provide a signal that can be from 0 to something depending on the asphericity of the neutron star. How is a neutron star an asymmetric device or a purely spherical device? If it is purely spherical, you have no emission at all. If there is an asymmetry, you can expect some kind of signal, but this depends on the asymmetry, and you have no idea. So predicting the signal from a spinning neutron pulsar is essentially super difficult. Even worse is the supernova. Because the supernova, if it is exactly spherical, you are dead. No emission at all, because it's a dipole. In order to get emission from a supernova, you need to assume that the explosion is not symmetric. We do know that it's not symmetric, so on that we are happy. But there is no model whatsoever capable to predict the size of the non-symmetry and the shape of the exploding supernova. So the signal from the exploding supernova could be from 0 to a relatively large signal without a definite prediction. The case of the supernova is interesting because sooner or later another supernova will explode in the galaxy. The last one was some time before you were born, 1987. I guess you were all born later than 87.
I was born in
87. So you were born, but you do not remember. But it was 1987 in the Large Magellanic Cloud is the last known galactic supernova. It's already 30 years, I'm sorry for you. So, but okay, I can be even more sorry, and that will be experimentally measured. So why we don't know, at least that we will know, because supernova can happen anytime, but the rate is known or reasonably estimated to be a few per century in a galaxy like ours. So probably during the lifetime of the next generation gravitational wave detector is reasonably probable that a supernova will happen, and also if we are not unlucky, we will be able to measure this event and understand what kind of signal you get. Actually, this is not completely true in the sense that if the supernova is very asymmetric, also the gravitational wave emission will be very asymmetric, and so nobody can tell how much gravitational wave will be beamed to the Earth. You could be unlucky and have a strong emission of supernova in the wrong direction. Of course, if you could have a sample of 1,000 supernova, you would be happy in the sense that you would solve the problem statistically. But if you get one event every 50 years, the problem becomes hard. So it is not obvious that supernova can be a good candidate. This is better. This is better because the signal is well understood. What is the problem is how many coalition neutron star binaries exist in the universe and how often do they coalesce? Answer, no idea. Why this? Because in principle it seems to be an easy problem. I compute the probability that a star become a neutron star. well known, because we know which star become neutron stars in a quite solid way, and so we can tell that a relatively large fraction of the stars will become neutron stars. But 30% of the stars are in binary system, so good news. 30% of a large number of stars become double neutron stars. Problem, this argument is wrong in the sense that it does not include one fact. That when a neutron star forms through supernova explosion, the other star, is it unaffected? Can you assume that binary stars behave like single star multiplied by 2? Very difficult to say. When a supernova explodes, depends on the state and the distance of the companion. If the binary system is binary but the two stars are not very close, probably you can just assume that the second star is not much affected, and so you can just multiply the probability. One star becomes a neutron star, then after a while the second star becomes a neutron star, and you are happy. But if, for example, the systems that are very close are disrupted by the first explosion, you never get very close neutron stars. If you get only very far away neutron stars, it could take 100 times the life of the universe to get coalition neutron stars, because if they are very far away, before they fall one into each other because of gravitational emission, it could take forever. So the numbers are very tricky here. And the message is, this is in principle a good signal, but we don't know how to make an estimate of the number. If the number is a few per century per galaxy, we are happy, because next generation detectors will probe thousands of galaxies by looking at the Virgo clusters. So they should observe between 10 and something events per year. So there is a strong hope that next generation experiments will be able to detect coalition binaries. But if they don't, unfortunately, the only conclusion would be that the number of neutron stars in binary system is smaller than expected. You cannot conclude that the gravitation theory is wrong. There is another signal that is more sure. That is the coalition not of binaries, but of the black holes of two galaxies that collide. You could consider at first that this is even less probable. Of course it is less probable, but there is an advantage. Fact number one. Essentially, all galaxies have a black hole in the center. It's a known fact. Second fact, galaxies do collide. There are many examples of colliding galaxies in the universe that are observed. Then, it is not difficult to compute the amount of colliding galaxies you get in the universe. This number is not that small because you integrate the whole universe. And the collision of two black holes, 10 to the 6 solar masses each, it's a huge signal that can be observed even if the event happens super far away. So the coalition black holes, not in the sense of small black holes, stellar black holes, but galactic black holes, is something that give a hope of detection, because estimates say that these should be visible with the next generation advanced detectors. At least not really maybe covering the whole universe, but covering a portion of the universe that is large enough to make a substantial number of events per year. What we know, the first